In this video, we're going to fix all the relays in this box which have failed with a really high contact resistance. The result should be more output power and much better receive sensitivity. Let's get started. All right, so these are the relays we're going to replace, and I've got new ones to put in. I should have bought one for this one. It's sealed, so maybe it'll be okay. Looks like all the contacts are connectorized, even the RF output, the power, TX drive, and this which goes to the other board. It's all in connectors, so it should be very easy to service. There's a lot of screws to come out, and of course the final transistors have their sets of screws too. Those will get taken out, cleaned, and then we'll put new paste on them. Let's start with all the connectors. This looks like the transmit drive right here. Got the receive over here. We could probably clean those up a bit. Transmit output, actually antenna output. It's a little oxidized. It looks like it's silver. So we got these three. That's an interesting little jumper. I never noticed that. It's coax. Check that out. That's a little coaxial jumper. We'll have to look into what that does. Let's pull this one out here. Oh, nice and easy. Just wiggle it. There it is. Not much is available as a service loop. It's pretty tight. Now the power connectors. Ooh, these are in good, and that's good that they are. Okay, that's the whole board. Now I want to be gentle with this board because it hasn't been out of this position in a long time. I don't want to stress the finals or other transistors. So I'm just going to go around and loosen everything before I take it out. Let it kind of rest in position for a moment. And ease into where it's going to go. Okay, I think this one does not need to be done ahead of time, but I think these will. This one may be just on the circuit board, we'll see. Same with this one. And these two look like they're, oh, these are transistors under the board that get soldered on top, so these do have to come out. Probably that one as well. All right, let's start with the loosening. That was very loose. Maybe some Loctite will go in here when we're done. Most of these do not have mica insulators, which is really nice because we can use a really conductive paste like Arctic Silver or something on it. All right, now for these guys. Okay, let's get these. Just gonna do a half turn. And when we're putting the board back in, these will be the first ones to get tightened. The rest of the board will reference this. That way we're not stressing the components. Okay, everything's loose. So now we'll just go ahead and take everything all the way out. Okay, we got all the connectors and screws out. It's wiggly. Let's see if we can figure out how it's supposed to wedge itself out of here. Doesn't look easy. There's stuff in the way in every corner. Over here might be the easiest, except for this connector, which has no service loop. Maybe if I take out the connector on the other side, I can pull it up. I might do that. Let's take this out real quick. Yeah, there is no service loop there. Let's just wiggle this, push out a little bit. Oh yeah, there we go. Now that can come over here. I should have put handles on it. All right, there it goes. Time for the big reveal. That's what's under there. And this is what's here. Look at that. So this big chunk here is a heat spreader. Like a heat sink, kind of. That's significant. That's like, yeah, it's almost half an inch thick. Iodined material. Maybe it's aluminum. Not sure. Yeah, this is probably where the longer screws went, if I had to guess. These holes are kind of interesting here. I still don't understand how this is supposed to get the heat out. There's no heat sink. I mean, with fins, you know, no radiative method. Here's where the fan is supposed to go, I think. They would just blow over that. I don't know. I've seen 100-watt radios with much more heat sinking capability. Kind of disappointed there. All right. Just taking a look at this board here, and look at this. I don't know if you guys can see it, but there is some solder migration here. And look carefully at these two joints. They're dark, really dark. I'm going to try to get a better angle on that. Well, it's hard to tell, but these joints have been overheated or something, and they're kind of dark looking around the interface between the solder and the metal. Between the solder and the wire, that is. So we'll take a look at that. This is the kind of area we're going to be working in to unsolder the relays anyway, so we'll be there quite a bit. So right away, I see a couple of interesting things on this circuit board. Let me show you something. I know this may be a little hard to see, but take a look at these solder joints. They were cut. You see that? Somebody soldered it and then cut it. And that's the case for pretty much all of these. It stuck out at all. Now, we know that you get a better solder joint if you trim ahead of time and then solder it and leave it alone. By cutting it after it dries, of course, you introduce the possibility of a crack because there's a lot of force going on when you make the cut. And you don't want to stress the solder joint and the vias and the PCB traces around it. So that's kind of surprising. Look at that one right there. I mean, it's just completely smashed. Somebody went through and just cut these things like crazy. That's the case all over this board. So there's a lot of potential for bad solder joints because this is the kind of thing you can't catch without like an X-ray inspection once you do it. That's why we always recommend trimming before you solder. Get it trimmed up real nice and then solder it in, leave it alone. That's how you get the strongest solder joint you can. Another thing that really seems like a deficiency here is this plate. This is the only heat sink the 4 MRF, whatever they are, the 4 power transistors get. And so if you're running 150 watts, there's no fan, there's no heat sink, there's just this heat spreader plate. Now, that could be okay in some applications, but let's talk about how this works. This is a matched impedance system. So if we have a 50 ohm antenna and we have a 50 ohm output impedance, that means if we deliver 150 watts to our load, we're also dissipating 150 watts right here. By definition, we have to in order to match the impedance. So 150 watts is getting delivered basically to this piece of metal. Now, how does this piece of metal get rid of the heat so that it doesn't just boil away? Well, there's 3 principal methods, right? One is radiative heat. That's where the metal actually emits heat coming out of the metal. Just like, say, if you have like a hot soldering iron, you put your hand over it, you can feel the heat. So there's heat coming out in an emission. But that doesn't really work too well in this application because inside the chassis here, inside there, it's just a bunch of shiny metal. So that metal will, of course, reflect the heat right back into where it came from. It's not going to absorb it really well due to the emissivity. You really would want a chassis that's dark and absorption, right? So that you could get that radiative heat. And there will be radiative heat here. This will get hot. You'll be able to feel it with your hand if you were, transmitting a lot of power for a while. So there's that. The other way would be conduction. If this was, for example, if it had some heatsink compound and it was sandwiched to something that could get rid of the heat, like a heatsink with fins, that would be fine. But in that case, in this case, it isn't done that way. I don't even think it's sandwiched that hard onto the circuit board. I think there's an intentional little gap here. I could be wrong about that, but in any case, there's no heatsink compound. And the thing it would be screwed to, this chassis here, it doesn't really have any cooling. In fact, it would be screwed to this part on the inside between two circuit boards. So at most, you're transferring the heat from one board to the other. It's just not really going to transfer a whole lot of heat, even if it does contact that really well with some goop, some heatsink compound, which it doesn't have any of. The other way would be what is basically another form of conduction called convection. If you're moving air across it, an air current, well, you can heat the air up and then the air can leave, and that brings some of the heat away. A lot of radios work like that. This does not have a fan, and because it's horizontal, it's flat, any heat dissipating here is going to naturally convect up to the circuit board where it came from. So it really isn't going to convect naturally, and there's no forced air. So I would say this is woefully inadequate for 150 watts, especially with a radio designed for commercial and marine applications, or paramilitary, like the advertisement says. All the radios I have, even ones that do a whole lot less power than this, have much more cooling capability. The IEC 706 has a heat sink and it has a fan. The IEC 736 has a huge heat sink and a fan. Let's see what else. The IEC 7300, heat sink and a fan. The IEC 718 has a heat sink and a fan. Two ICOM commercial and marine radios I have, the ICOM M700 and the ICOM M600, both have fans and significant heat sinks. So what were they thinking? Well, for one, they did sell a fan kit, but it's not even clear to me exactly how that would go on. And if you had a fan, what would you do? Like blow air, right in this gap here? Would you blow air into that? It's just not set up. If this had like ribs in it, you could at least double the surface area. If somebody cut some trenches into here like that, then I could see, maybe getting some good convection out of it with a fan. But it's just a panel. So I'm going to say this is woefully inadequate. And when this radio was built, other companies, lots of companies, made radios with better heat sinking technology. It's not like they didn't know how to build a heat sink. The knowledge was there, they just didn't do it. I don't really understand why that would be. And it's a shame, because the rest of this radio is overbuilt nicely. These power transistors, for example, you could dissipate almost 300 watts from this board with these transistors. It's really nicely over-spec'd. I love the way it's balanced and the bias adjustments and everything. The relays, yeah, I think you could do about 200 watts through these. But with the lack of cooling, I don't know. I think you'd have to be very intermittent. If you were to calculate, how hot this plate will get.
This is the W6
Hold on.
Peter.
If we wanted to, we could look at the heat capacity for a hunk of aluminum with an iodine chem film across it, and we could calculate basically how hot this will get given a 25 degree ambient temperature and so much power getting dumped into it in the center here. Basically, the temperature will go up and up and up because there's not a really good method to release the heat from this structure, right? It's just going to get hotter and hotter. So in order to use this radio, you must have a low duty cycle. It is simply not designed for high duty cycle. So at 150 watts, I would say you wouldn't want to key down for more than about 5 minutes, maybe 10, with constant power. With talking, of course, on sideband, it's a low duty cycle and you get away with it. So if you're using this radio for a digital mode, like FT8 or something, you really need to scale the power back and or add a fan. This is where I think a fan should go if you were going to add one, but there's no mounting hardware for it. There's not like inserts or anything to screw a fan into, not even holes. There's this. I guess you could bring that out into a panel and then put a fan onto that. It would just kind of rattle. I don't even see a good way to put a fan on here. And there's not room inside it because the circuit board goes against here, and you're not really cooling under the board like you want to. Most of the fan would go over the board. So I don't know. They've got these holes in here. You see that? There's a pattern of them that go around. Let me show you. There's a pattern that go like this, and the heat sink, the heat spreader goes right in the center here. So I guess around the edges you might get a little bit of convection, which would help you heat the other circuit board up where the computer is. Yeah, it doesn't seem great. But okay, enough about the deficiencies. What we came here to do is replace these relays. So let's start unsoldering them. I'm going to spare you the boredom of watching every relay come out, but I am going to take one out so we can see how it looks. That's the power side. This is the RF side over here. Look how long this trace is here, all the RF goes through. I'm hoping to kind of wiggle it out. The problem with solder sucking is you lose all your conduction into the via once you suck all the solder out. There's always one little bit that stays in there. There we go. There it is. Let's compare it to the new one. See if I got the right one. Okay, there's the original, here's the new one. They look pretty similar. Same arrangement of terminals down here. Looks like I broke one off, so maybe I need to improve my removal technique. The pads look beautiful in here. They're not burned or charred or anything. See how nice and shiny that is? And if you look at the old one up close, you can see it's dark inside there. Look at that. Let's just go ahead and break it. So you see how it's been arced or something. But that is why I was getting hundreds of ohms of resistance sometimes between different bands. So let's replace it. Oh yeah, that looks right. Some of the holes are a little tight, but a little solder will get it in there, as you see right there. That's the right footprint. I'll put the model number of the relay in the description so you can buy these if you need to. You can buy them new. That's what I did. Should be good to go for a few years, right? All right, so I'll pull all these out, clean them up, then we'll put these in. One thing I do like is I'm seeing via stapling here. That's an effort to get even more conduction and more stability in the circuit. And in this case, a better ground plane by connecting the two planes from both sides of the boards together multiple times along the way. Not just one little via somewhere, but every centimeter or so there's another one. Well, I got all the relays out. There they are. Probably save them and do something with the coils. Kind of neat looking. Now I got to clean this up with some alcohol. Well, I got it all cleaned up. It took a while, but everything's clean here. What it turned out was going on with this, there's actually a spot on the board that doesn't have any mask. So copper was exposed and somebody put some solder over it. And then over here, this eyelet kind of popped out a little bit, so I scraped away some mask and I'll put something across it when I put the relay in, because that is where the RF goes. Otherwise, though, I think it's about ready to go. You can see how it looks without the relays. All right, there it is. First one is pushed through. Just needed a little bit of wiggling. I gotta solder it in. And of course, we'll clean those up when we're all done. Okay, there it is. Everything's all cleaned up. I resoldered a lot of the OEM joints that were kind of weird as I mentioned before, they really aggressively cut a lot of these solder joints that didn't need to be cut right after they had formed, which is bad. You're never supposed to do that. And it was not necessary because they had almost a 1/2 inch clearance to the chassis. There's no reason to trim all this like that. Even integrated circuit points were trimmed. I don't understand why. So I went over some of that, made it look a little bit better. Yeah, this one can't be helped. It's just going to look like that. But the rest of it looks pretty good. And I think now it's time to install it back into the chassis. Take one last look. Quite a finger trap there. There we go. Now I just gotta screw it in. So here's the deal with the heat sinking. The heat sink does contact the chassis right here. It sits down upon it. And so that does give it a chance to spread the heat to the board on top. Remember, this is upside down. So you're heating up the computer and the oscillator and the receiving circuits with the heat from the transmitter pretty well. And then as it travels outward, it gets over to here to the edges. That's the path of conduction for this. Not the best path. And I really think probably after we do this mod and verify that these low pass filters are working again, then I'll go back and enhance the conduction with some paste under here, maybe with a fan as well. We'll see. All right, that's all put together. Now let's test it out. Everything is connected. Let's turn it on. So far, so good. Now this is with the internal speaker. I don't have the external one hooked up, so it doesn't sound as good as it can. Did you hear the relay snap there? I couldn't get this before. Alright, so what we have hooked up here is the low pass filter board that we just repaired. And I have the output of it and input of it connected to this piece of equipment here. That Marconi will do a 2-port analysis and show me which frequencies are passing through. As you can see right down here, I've sort of hacked the analyzer into the circuit using some clip leads. It works fine. And let me show you what happens as we change frequencies. So the first thing I have to do is turn on the tracking generator. That generates a signal that goes through the circuit. And right away you can see the passband. So right here is where it's falling off. The radio is tuned to 5 megahertz right now. And so that puts it into position B on the filter board. I'm sorry, that puts it into position C on the filter board, which cuts out at 8.9 megahertz. Let's see if we can verify that. This is what didn't work before, by the way. Let's see, marker. So right there, it's like about 10 megahertz, 9.9, and it's cutting off after that. And the idea is a signal transmitted in this band will not have harmonics that go over, and well, will have harmonics over here, but they get cut out significantly by the filter. We're looking at 10 dB per division right now, so you can see we're 2.5 divisions lower, so 25 dB for rejection approximately. And if the PA amplifier is functioning properly, that is going to be enough to bring the emissions into spec. So let me show you, for example, what happens if I switch to, say, 15 megahertz. There we go. So you see how it moved over. And let's see what frequency that is. Looks like the cutoff happens at right around 16 megahertz. So the harmonic of 15 megahertz would be 30 megahertz. And by the time we get to 30 megahertz, we're over the cliff. Nothing's going to come out over here. So let's check the other bands real quick, because this is where the sensitivity of the radio is really falling apart. And I'm going to start with, basically, I'm going to go just below the cutoffs for each of the bands listed in the manual. So, okay, filter band A cuts off at 2.8, so let's go to like 2.5, program frequency. There's that. Let's go to 4.4. Yeah, okay. 8.9, but just below it, so let's do 8.8, program frequency, 8.8. Yeah. Okay, 15.5 is the next cutoff, so we'll go to 14, or just 15, yeah. Okay. 20.6 is the next, so let's go to 20. There we go. And then the last one cuts off at 30, so we can just go to like 29 megahertz. There it is. Got a little bit of loss there. Let's see how much. Oh, this is at like 30 megahertz, so over here at 29, 28, we're okay. We touched briefly on why I don't like this design, but let me clarify a few points about this, okay? This is a design issue that affects the SGC 2020 as well, but I've never seen it on any ICOM, Yaesu, or Kenwood radio. Basically, the receiver is listening through the transmitter's low-pass filter. And that's good because it blocks off frequencies that are higher than what we're listening to, so you will not be hearing traffic on higher bands on lower bands. The problem with this approach, though, is there's not a bandpass filter, so there's not a high-pass filter. And so when you're on, say, 10 meters over here on the spectrum, you're still going to have RF from lower frequencies, the AM broadcast band, shortwave bands, all other bands, leaking through the circuitry because they're not being blocked off right away. And sometimes more sensitive parts of the circuit can be susceptible to signals leaking through that way. And this radio has a weakness for image rejection. You'll note that in a lot of reviews of it. And this is why it doesn't have a cutoff on this side, which it needs for the receiver. The transmitter doesn't need that, and so you can understand why it's not part of that board. Although I do wonder if we could put a capacitor into the filter to gently cut off some of the lower bands, and that might buy us a little more dynamic range. Anyway, that's why most radios have a dedicated low-power bandpass filter for the receiver section. It's usually made of very small components, and they use diodes biased with DC for each band to cut them in and out. And that's what this radio really could use. If it's connected to an antenna coupler like the SGC 230, then that kind of provides some of that filtering, but it would be much better if it was just built into the radio. Okay, I adjusted this so we could see it a little bit better. And now you can see the total rejection is, 1, 2, 3, 4, almost 50 dB in the low-pass filter, so that's excellent. Okay, so let's do a sensitivity test real quick. This is my signal generator, the HP8647A. It's going to make a very small RF signal, simulating a weak signal, going into the antenna port on the SGC SG-2000. The audio output from this is coming through the Telex connector. That's going to go over here to the audio input of this Marconi, which I'm using just as a SINAD meter. All right. So first what we want to do is dial everything into the same frequency. Let's go to the 20 meter band. Program frequency 14.2. All right, now we're going to do that up here as well. Frequency 14.2 megahertz. And you see that's also what I've got dialed in on the SGC 2000. Let's turn up the audio a little bit. You can hear that nothing's coming through right now. Now what we need to do is we need to tune off to the side a little bit and turn on the RF. So let's turn on the RF first. And we're going to crank the amplitude up a bit. And we'll go on here. There we go. Now the first thing I have to do is match the frequency so it's definitely the same tone. The SINAD meter is dialed in for 1 kilohertz. And so if there's a frequency offset between them, I need to correct for that, which I'll do real quick. We see that we're off by about 42 hertz here. So let's get that just right. Okay, that looks pretty good. And you see our SINAD right now is 21.1 dB. And we're going to lower the amplitude of this generator until we get to 10 dB. So I'm just turning it down here. You see that? Dropping a bit. By the way, this is averaged among 4 readings or 5 readings or something, so we wait a moment after we make an adjustment. Here we are down at minus 120. Okay, there we go. So yeah, about 12 dB SINAD. I'm gonna go a little bit lower. And 10 dB SINAD is really where it starts to fall apart. And you see we're at 10.5, 10.6 right now. Go a little bit lower until this is kind of flickering right around 10. We're at 10.1. Of course, we always want to push it as far as we can. Okay, here's 9.9. Go a little higher. And if this is 10, we'll probably leave it here. Yeah, that's about 10. I'm going to press microvolts. And so that's 0.188 microvolts. If you see right here. That's pretty sensitive. That's quite good. And so I'll post the results of all the common hand bands here when I do the editing, and you can see that indeed the radio is quite sensitive everywhere except perhaps on 160 meters where the broadcast band filter is cutting it out. Alrighty. After the sensitivity testing, I looked at the harmonic output of the transmitter, and I'm happy to say all the bands are in compliance. The harmonics are more than 50 dB down from the carrier. So that's really good, and it means that the new relays are doing their job with the low-pass filter. That's all for this video. I think we'll address the design deficiencies in another video, and we'll also be working on the head unit soon to improve the audio. Thank you very much for watching. 7-3.